a glimpse at vector calculus. So this is the third chapter. And we've already started on this, right, and the del operator. We don't go too deep into vector calculus. It's not a full course on vector calculus. You can do courses like that, but this is just a glimpse, okay? So what do we know already about vector calculus? Well, we've got the del operator. Okay, and we've combined that with functions of 2 or maybe even 3 variables. Okay, so for example, you might have a function of 3 variables, right? And you can talk about the gradient of that f. So you apply the derivative to each part and you form a vector. So for this one, it would be something like d dx of all that, d dy of all that, and d dz of all that. Okay? So that's nothing there. Okay? So that's the only operation we really know at the moment. I'm not sure what it means, but we talked about it representing a normal vector, right, when we did Lagrange multipliers. Okay, so we're going to look a little bit more into that today. Hello, welcome. We're going to look into that a little bit more today, all right? So remember back to first year. I won't do this too much, but don't forget about the vectors that you learnt in first year, okay? Things like the dot product, the cross product, normal vectors, tangent planes, all that sort of stuff. We will draw on that every now and then, so-called vector calculus, okay? So you may need to just remember back to 1131, or you can ask me, or whatever. Okay, so let's start. So okay, let's say I'm in 3-dimensional space. And instead of a surface, I'm going to have a curve. Okay? So you can think of this as being simpler than a surface. All right? So to get a curve, let's form a whole set of points. Okay? So I'll call that, I don't know, the curve curly C. Now, at each point there, it will have some position, right? So there's an x-coordinate, a y-coordinate, and a z-coordinate. Okay? And what we can do, we're going to use vectors, we can form a vector from the origin to any point P on the curve. Okay? So it might look something like this. Okay, so in this case, t would be our parameter. Maybe it's time, maybe it's something else. And as that parameter varies, your vector moves, right? And the tip touches the curve, okay? Right? So, you know, r of t could be something like this. Okay, so x, y, and z are just functions of one variable, just real valued things, t squared, cosine t, 1 on t, whatever. And as t moves, your vector moves. Okay? So let's think about a simple example. I don't know, it could be something like this. Something like that. So the x component is t, the y component is t squared, the z component is t cubed. And as you vary t, your vector will change, right? And it'll map out some curve. Okay? So it's a vector function of one variable. The only variable there is the parameter, the time. Okay? So in some cases, it's very similar to what you already saw at school, except now you're working in three-dimensional space with vectors. Okay? So, what can we do with this amazing, amazing framework? Well, I'm glad you asked on a Friday afternoon. Okay? It's called vector calculus. So what do you think we can do with that kind of vector function? Yeah, hang on. I'm pretty tired, hey?
Calculus.
Yeah, such as? So what, for example?
Well, we could find the rate of change. Yeah. So we could find velocity.
Yeah. Yeah, we can differentiate it. Do. Question. What we do? What else can we do in calculus? That's it, Friday afternoon. Yeah? We can talk about velocity, acceleration, you know, all those ideas from that are related to physics, right? Work. We can talk about work done, about all sorts of stuff, right? So with these vector functions of one variable, we can do a lot, okay? We're only going to have a quick look at it, but we can do a lot. So for example, if I was differentiating, I would just differentiate everything with respect to t and just form a new vector. That's a 2. Oh, my internet sucks. Okay. Mine does too sometimes. Isn't that really shocking? Like we're supposed to live in a first world country, you know, and the internet's you go 50k out of Sydney and it's. I had some Chinese professors visit me a couple of years ago here, and they're looking around at all the buildings like, I think I've stepped back into the second world, you know. It's like, yeah, you have better stuff than we do. Anyway, so there's no tricks. There's no tricks here, just regular calculus on vectors. Now, okay, here's a good question. What do you think this new vector does? What is its relationship with the curve? What do you think? Just as a guess. Anybody know? What do we usually geometrically associate derivatives with? Gradient, tangents, slopes of tangents, right? With this one, so you're on the right track. With this one, the derivative is going to be a tangent vector to the curve. Okay, a tangent vector to the curve. So if I differentiate it, it might look something like this. Okay, and that will change. I mean, the angle's not necessarily 90 degrees between the two vectors. That's just the way I've drawn it. Okay. Okay. Kind of agrees with what we already know from school. Okay? You can talk about the length of these vectors. So you can talk about speed, right? If it gives you something related to displacement or velocity or acceleration, you can work with those. Okay? So, questions?
If you take the derivative of the green line, would it not be the same thing?
Yeah, but geometrically, what does it mean? I guess, yeah. So you can talk about, oh, I've got all these points on the line, I'll just treat them as functions and differentiate, 100%. But I'm just trying to work out, okay, if I've got a vector that's linking to the origin, and you can look at these things in different ways, right? So what you're talking about is sort of component ways of thinking about it, and forget about the I, J's and K's, just write them as a list, right? I'm saying because it's vector calculus, I'll do the I's, J's and K's, okay? That's good, really good question. So just remember, what's the I, J and K vector? And I know, you know, people have different notations. Okay? Now the I is not the same I as the complex number I that you see in first year. Okay? All right, let's do some problems. Let's actually have a look at today's class notes. Any other questions before we get started? Okay. Let's start. Any questions at home? Audio is stuttering a bit for me. Oh, I wonder if it's because I walk around. I wonder, if I go over here, tell me if the audio drops out at home. I'm just in the zone about now, I reckon, somewhere around here. Let me know at home. I won't run around so much. Thanks for letting me know, by the way. So let's have a look at today's problem. Bop, bop, bop. Okay. This is a typical problem you'll see in tutorials and in the questions that I have put together, those 100 or so questions. Here's a specific example of a vector function of one variable. Now, in this case, I'm only working in two-dimensional space. Okay, you see how there's no sort of third component in that box? So you've got 2 cos t, 3 sine t, and nothing else. So we're only in 2 dimensions here. Okay? So what does this look like? Well, I'm glad you asked. So the way I think of this, that's your x, that's your y. So x equals 2 cos t, y equals, 3 sine t. And the idea is to try to work out what curve we've got here. Okay? So we know a relationship between cosine and sine. If we square them and add them together, we get 1. So that's a handy thing. So let's try that. So I'll make cos the subject and sine the subject. Okay, so we've managed to eliminate the t's, the parameter. And if we think back, this is going to give us, well, this is the equation of an ellipse. Okay? So when y is 0, x will be 2, right? And negative 2. And when x is 0, y is going to be 3 and negative 3. Okay, so if we draw that, we'll get something like this. When x equals 0, sorry, wrong way. Yeah, that's my badly drawn ellipse. Okay. Okay. All right. What else? Sketch and describe it. I've sketched it badly. I've described it. It's an ellipse. Nothing more to do. Okay? So, next part of the question. If a particle moves along this curve, so here would be our, our vector r. Okay? If a particle moves along this curve, calculate the derivative, right? So what we're essentially doing here is forming a velocity vector. Okay, so for these ones it's pretty easy. Differentiate with respect to t, your original expression. Okay, so it's going to be -2 sine t, 3 cosine t. Okay, you can write that with i's and j's if you want, but that's okay. An ordered column or an ordered row, that's fine. Okay. Is the speed constant? Okay, so what do we mean when we talk about speed? So if you think of this as a velocity vector, we can look at the length or the magnitude of this thing. Okay? So how do you work out the magnitude or the length of a vector again? I've forgotten. How do you do it?
Square root of x squared plus y squared.
Mm-hmm. Yeah. Yep, exactly. Thank you. So square the components, add them together, take the square root. It's Pythagoras, right? So let's have a look. Okay, so looks like we might have a cos squared and sine squared here. But unfortunately, hi, welcome, you made it. Unfortunately, is this constant? Can we simplify that down to just a number? No, we can't. It would be lovely to do it, but we can't do it. So what does this tell us? It tells us that the speed varies, the ellipse. The speed varies. Okay, so is the speed constant? Speed is not constant. Oh. Okay. Last one, calculate the integral. Now, sorry, let me put that up for everyone at home. Calculate the integral. Now, it's not clear what this means at the moment, okay? But how do we integrate a vector-valued function? Just integrate, okay? Just integrate each part separately, and you'll get a vector as your answer. But it's not clear what it actually means. We will do stuff with this, but at the moment, let's just do it and see what happens, okay? So let's just do the third part and see what happens. Okay, so you integrate the first component, you integrate the second component, and your answer will be some vector, some constant vector, right? So integrate cosine. You can probably do this using symmetry, right? But I'll just do it. Okay. Oh, sorry, path. Oops. Gone off the page. Okay. So simplify that, you'll get, what did I get in the answer? Yeah. So you can use symmetry to simplify it. Okay. So nothing super difficult about this, as long as you remember to work on the components separately. First component, second component. Apply the integrals or the derivatives to them. Okay? So it's not clear what we've got, but we will give some meaning to integrals. Questions? Questions? Let me have a look at home, see what's happening. Yeah, I think it does. I think, sorry, I put this up for everyone at home. Audio starts to cut out when you walk further away. Does that mean everybody has to sit closer then? You know, how am I going to, I need to like have more microphones. Okay. Yeah, it sucks. The audio is the most important part, I think, for many people, especially on YouTube, right? If you have bad audio, it's hard to understand what's going on, right? Okay, so. No, not for me. Audio, fine. Oh, question. Hang on. I'll come up here and we'll see if the audio cuts out again. Yeah. Is everything okay? That's all.
Yeah, sorry, I missed the last lecture. What's the line with the pi on the top and the minus pi on the top do?
Oh, so when you integrate, so that's just my shorthand of saying, so it's a good question. So sometimes they write it like this. So let me just go back for everyone at home. They write this big bracket. And so it's this evaluated at t equals pi minus this evaluated at t equals negative pi. Okay? So if you can do sort of standard integrals, that's usually, well, that's some of the notation that's used. Okay? Other questions? All right. Let's do another one. Yeah. Oh, no, not that one. I've got too many pieces of paper. I'll just show you this one quickly. We'll come back to gradient of a vector field. Right. Here's one that I prepared earlier. Okay? So this is one that I just wrote out shorthand. So same sort of question, just a slightly different vector function now. Okay? So now you've got a curve sitting in 3D. Okay, so who can tell me, what is the dimension of a curve? What is the dimension of a curve? Who can tell me? It's not a trick question. How many dimensions does a curve have? Yeah.
2 dimensions?
No, close, close.
1 dimension.
1 dimension, right? Think of the number line. The number line. How many dimensions does the number line have? 1. You can go that way. You can sort of go, say horizontally, right? You take the number line and you twist it and curve it. Still got one dimension, but it's sitting in either two-dimensional or three-dimensional space. Right? In this situation, see the spring up the top? It's one-dimensional, but it's sitting in three-dimensional space. Okay? Okay. So, same sort of deal. This is what's happening in the XY plane. Okay? That's not correct. Okay, so it's just a circle. Oh no, it is. It's a circle. Yeah, it is. That's the angle T. Okay, so if you let Z equal 0, right? So T equals 0, what's happening? It's just going around, you're looking down on it, it's just going around and around and around. Now, as T increases, you're going up or down the Z-axis, depending on whether T is going positive or negative. Here it's non-negative. Okay? And the calculations are the same. Okay? So once we've worked out what this actually is, you can calculate the derivative, you can calculate the length, it is a constant, and then you can do an integral. Okay? So these are basic standard, basic standard calculations. Let's go back. Why did we take the integral from negative pi to pi? Just because that's, no reason, just because I wanted to put some numbers in there. No particular reason. Okay, just for illustrative purposes. Still fine, okay, good. Oh, audio is ahead of your written answering. So if the stream slows down, what I usually do is I go, I can't handle this anymore. And then if I want to, I just open it up again. Okay, or you can just mute me, right? That's fine. Okay? So if you don't know about vector-valued functions, now you do. And you can do calculus with them, which is brilliant, right? Because calculus, you can do many things. Okay, limits. Okay, I reckon it's right there. Is it cutting in and out now? Let me know at home. How would you take the limit? I've got my R function, my R vector valued function. How, bless you, how would I take the limit? Let's say T approaches 0. How would I do that? What do you think? Based on what we've done today, what do you think? How would we do it? Gesundheit. That's a dead spot. Any ideas? If I asked you, what is the limit of R of T as T goes to 0? What kind of ways of working? Yeah, just take the limit as of cos T as T. Take the limit of sine T as T approaches 0. Take the limit of T as T approaches 0. And what's your answer going to be? It's going to be a vector. And it'll be something like 1, 0, 0. So the limit will be a vector, just like the derivatives, just like the integral. You put a vector in, you get a vector out. Okay? Other questions? Okay. Not difficult, but you need to know what to do, right? Okay. Yeah, okay, all right. There's a couple of dead spots in, so people are saying it's cut out. There's 2 dead spots in this theatre. I know where they are. There's one there and there's one there. I will avoid those. I'll try to. Thanks for letting me know. Okay. Yep. Second part of this lecture. Let's talk about the gradient of a vector of a function, the gradient field of a vector function. We've already talked about this in the previous lecture. Okay, so we've talked about the gradient when we did Lagrange multipliers. Okay, so just to remember, the gradient is this, right? Let's say it's three-dimensional, a function of 3 variables. Okay, so we say gradient or grad f. We use this del operator, that triangle bit, and we get a vector for it. Okay, and we talked about what this means geometrically. So, for example, let's say I've got some sort of surface, and this can be, I don't know, f equals, you know, a function of x, y, and z, and we set it to a constant. And P, for any point P on the surface, this gradient vector is normal to the surface, okay? So why would you want to know that? Well, it will come in useful. All right, so let's make this a little bit more definite by doing a particular problem. Okay? Here's a function. X squared plus 4y squared is a function of 2 variables. And we're asked to compute the gradient of that. Okay, so it's not difficult. Let's do it. So it's going to be a vector. In this case, it's only going to have 2 components because f is just a function of 2 variables. So I take my partial derivatives, apply it to f, I'll get a vector. Okay? So 2x and 8y. And if you don't want to write it as a column or a row, you can use i's and j's. It's up to you. Okay, so depending on where you are on that surface, this gradient vector will point in different directions and it will have different lengths. Okay, so pretty easy. All right, the second part of the question is more difficult. Show that the thing you calculated in part 1 is normal to this equals a constant, right? So here, this surface is just the general layout. But let's make it a little bit more definite now. Okay. What is this curve going to be in the xy plane? Who can tell me? What kind of curve is it going to be? We just looked at one. It's definitely curvy, so, and an ellipse, okay? An ellipse, you're absolutely right. Okay, so this is an ellipse. So how do you parameterize an ellipse? With cosines and sines, right? Okay? Let's rewrite it like this. Yeah. You don't have to do that, but it helps you with choosing your parameters. Okay. So let's make a vector out of it. At the moment, we're in the component world, like you were talking about before. We don't care about i's or j's or whatever. We just have a list, x equals this, y equals this. Okay? But let's combine them and actually make a vector. So consider, please. Okay? Now, what do we need to do? We want to show that the gradient vector, grad f, is normal to the curve. So what is the relationship between the r vector and the who can tell me? If we want to show something's perpendicular, what's one way of doing it using vectors or some operation in vectors? Dot product. And the dot product should be 0, exactly. That's first year, right? Or even like high school. So we basically want to take the dot product of the gradient with the r vector and show that it's 0. Yeah? So I've introduced it, right? I've said this and this represent points on the same curve, because you can use cos squared plus sine squared equals 1. Okay? All right. So show. That's basically what we want to show. And this is on the curve, this is on the ellipse, right? So in our original grad f, we want to replace x with 4 cos t, y with 2 sin t. Okay, so we're only talking about points on the ellipse, not anywhere else. Where did my pen go? That's what I have to do. Okay, so on our ellipse, that's true. So let's go up here and replace x with 4 cos t, y with 2 sin t. Oh, sorry. Okay. So 2 times x is going to be 8 cos t. 8 times y is going to be 16 sin t. And we're dotting it with these two things. Okay. Oh, hang on. Oh, not that. The derivative. Okay? Not that, the derivative. Let me draw you a picture. That's what we want. Okay? We want the angle, not to the r, I got confused, we want it to the derivative, the tangent, right? So let's see. So r dash, this is going to be, okay, we differentiate that. We differentiate that. Okay, so what are we going to get? We're going to get negative 32 cos t sin t plus 32 sin t cos t. Whew. Okay? So, what do we know? These two vectors must be orthogonal, perpendicular, normal, whatever word you want to use. Okay? And so okay, that would be our conclusion. Now there's a third part to this question. It's quite involved, so I'm going to leave that. We'll take a break, come back in 10 minutes, come down and ask me questions, get recharged, grab a cup of coffee or something. If you're at home, you know, something nice. And, let's meet again in 10 minutes, okay? Come down with questions if you have any. Okay. Okay, we've had the tech team on the case here, helping us out. Let me just go for a little wander, see if it works. Looks good. Sounds good. Yeah. Sounds really good. Okay, so I wanted to spend a little bit of time talking about the third problem. So the third problem is important, okay? And we'll do some revision and a few of the, maybe some of the Mobius questions or whatever in this class. But before we get there, I want to talk about a super special kind of derivative, okay? Now, last week, somebody came up to me and they said, hey, can a function change in any direction? Can a surface change in any direction? Right, so we have things like df dx, partial derivative, df dy, partial derivative, but they're only in two directions, right? What about in other directions? And I said, we will talk about that. So now is the time that we're going to talk about that. So let me start this off with a picture. Okay? If you can understand the picture, you can understand the idea. The terminology, calculate the rate of change, the directional derivative of f at a point in the direction of this vector. Okay? So let's slow down a bit. You've got a surface or a curve, and you want to understand the rate of change at a point on the curve or the surface in a particular direction. Okay? So let me show you a picture, because I think a picture is pretty good. Okay. Here we are in three-dimensional space. Welcome. I've got a surface, z equals x squared plus 4y squared. Okay, so we're not making it constant, it's just a surface. Okay? All right, so think about the question now. In the direction of the vector u is 1, 1, or I plus j. Okay? So if I draw that vector in the picture, what does it look like? Well, oh, hello. There it is. Okay? It's in the xy plane, that's fine. And it's pointing in a certain direction, like vectors do. Okay? Okay, so how does this relate to the slope of a tangent or whatever? Let's take the plane that is parallel to the vector. Okay? Let's take the plane that is parallel to the vector. Bam. Okay? Can you see that it's not parallel to either the x-axis or the y-axis? So we're not talking about partial derivatives here. We're talking about something else. Okay? We're talking about something else. So, what do we get when we smash the surface and the plane? What do we get? We get a curve, right? Looks like a parabola. What do you think this directional derivative is going to measure at one of the points on the parabola? What do you think? Bro, you're watching that? Put that away. Come on, I'm right here. Yes, redeem yourself.
Is it like the derivative of the parabola?
So geometrically, what would we be talking about for the derivative of the parabola, geometrically?
Would it be just like the equation of the curve?
No, close. You're warm. The slope of the tangent. I think that's what you meant, right? I think that's what you meant. So let's have a look. We've smashed the two together. Let's look at the intersection. Okay, you see how it's not parallel to any of the axes or any of the planes containing the axes? That, I think, yeah. So we want the slope of that parabola, slope of the tangent at the point A. That's what you're doing when you're calculating these directional derivatives. Okay? So if you can picture it in your mind or on your screen or whatever, that's what you're doing. Okay? I think a lot of students do this course and they can do the mathematics, but actually understanding what it is you've calculated is not always there. Okay? So how do you do it? How do you do it? I'm glad you asked. Okay? So most of the derivatives are slopes of tangents to a special curve, and you get the curve by smashing a plane into a surface. If you can understand that, that's it. Okay? All right. Calculate the rate of change of this function at this point, so let's call that P, in this direction. Okay? So the notation we use is the doof notation. All right, actually, hang on, let me adjust that. So the U has a little hat. The U's a vector, and this is just a capital D. Okay, so it's shorthand notation for directional derivative of a function in the direction of this vector U. Okay, but what is it? It's the dot product of the gradient vector, here it is again, with a unit vector in the same direction as U. Okay? Why do we have a unit vector? Well, we're talking about rate per unit change. Okay? You don't have to define it like that, but that's the way we define it. Okay? So let's think back to how you get a unit vector. Right? You take your original vector and you divide by its length. Okay? So, what does it look like for this particular problem? I'm glad you asked. Okay? Here, P is the 0.11. U is the vector, I plus j, or 1, comma 1. Let's compute the unit vector associated with u in the same direction, and let's compute the gradient of f at the point P. Dot product, inner product, scalar product, whatever you want to call it. It's a big, huge dot. Okay, let's go back up here. We've already got our gradient vector, but we want to evaluate it at x equals 1, y equals 1, because that's our point of interest. That's our point of interest. You up there. Okay, so this is going to be 2, 8. And what's the length of this vector here? Who can tell me? If the vector is 1, 1 or I plus j, what's its length? Root 2 is perfect. How do you do that? You take the components, you square them, you add them together, and you take the square root. Okay, so we're dotting. Okay, think back to the dot product. How do you do a dot product? I've forgotten. Well, you work with the components. 2 times 1 plus 8 times 1. And you multiply by 1 on root 2 in this case. Okay? Note, our answer is a number. It's not a vector. We would expect it to be a number. Why? Because it's the slope of a tangent line. Okay? It's the gradient of a tangent line. So we've got a number. Big deal. The number is positive. What could we say about our function? Would it be increasing, you think, or decreasing in that direction at that point? Increasing, right? Increasing. Let's go back to our picture. We can kind of have a look at our picture and see what's happening. Okay. Fit a tangent line there. Going along here, it's definitely increasing. Yeah? You can kind of just see it from the graph. Gosh, GeoGebra is so good. It's just incredible, hey? Questions? That is a very classic, common problem. Here's a surface, here's a point and a vector. How's the surface changing at that point in the direction of a given vector? Okay, that is a classic 2019 problem. Okay? Questions? Yes.
Could you clarify how you got the direction of the plane? Like, how do you know it's vertical and not horizontal? Also?
Yeah. So you need. So yeah, good question. I've done it so. There. So that's a surface that cuts. That's a plane that cuts the surface, right, to form a curve. Now, if I had my surfaces going the planes going the other way, they might not cut the surface, right? Yeah, and it contains the vector in question. Okay, and the vector has a direction, so we know whether we're going like that or turning around and going the other way. Okay. It also contains the point A, right? Other questions? Good question. Okay, so that is really important. You'll see questions like this in Mobius Week 3 quiz. And I don't know if I guarantee it, but they're pretty popular lab test questions as well. Here's a surface. Here's a vector. Here's a point. How is the surface changing at that point in that direction? Okay? Super, super, super. Come on, man, at least pretend like you're paying attention. Is it okay? It's not long to go now. You want to ask a question?
No, I don't.
Not yet. I'll come back. Okay, so it's important. It's very, very, very important, this kind of question. All right, let's see what's happening at home. Hang on, there's a good question. Wait, sorry. Okay, how is the vector gradient meant to be perpendicular to the surface at any point P? So, so when we talk about the perpendicular, we're talking about specific values of your function of 2 or 3 variables. So we call them level curves, okay? So that's the difference. Here, we're not talking about level curves, there's just a surface, okay? We're not saying, f equals 16 or something like that. So that's the difference. All right, let's do some revision. Okay, these are problems picked by moi from, I think they might be from next week's Mobius, or at least they were from week 3 in 2024. Okay, so let's work out what we do for these kind of problems. Okay, so this is like revision for the last 2 lectures, 2 or 3 lectures. Okay, you've got a function of 3 variables. Sometimes it's called a scalar field. You can call it whatever you like. It's not vector valued. It's a function of 3 things. Okay? Compute the gradient of phi. Okay? So we've got a scalar function, a function of 3 variables. We want to turn it into a vector, and basically we do that using the del operator and the derivatives. Okay, so let's work through it and see how we go. So that's our operator. That's what we apply to phi. Okay? So let's do it, then we can write down what we get. Okay. So let's see, how difficult are these partial derivatives? Not too bad. Okay, so the first one, differentiate that mess with respect to x. So that's going to be 0. 3z squared is going to come to the front, and I'm going to divide by that. 3z cubed, sorry. Okay, so we're going to get a bit of cancellation there. What about d phi dy? What's that going to be? Who can tell me? Who can tell me?
Two y's to the power of 4.
Yep, so the y squared is the only y in there, so imagine everything else is constant, 2y times z to the power 4, exactly. And finally, differentiate with respect to z. So that's going to become 4z cubed times y squared. And then over here, the 3x is going to come to the front and everything on that's going to come to the bottom. Oh, hang on, no, 3x times 3z squared. Okay, and now it's just simplification. So the first one's going to be 1 on x. Something like that. Okay? So it's a bit of a mess, but you know, we can get there, we can put in the components and we're done. Okay, so it's really about, you know, just can you differentiate? That's really what it is. Or have I made a mistake?
I'm pretty sure that that 1 over z component is supposed to be a 3 over z, isn't it?
Let's have a look. Let's have a look. Oh, because there's 3 squared. Yeah. Thank you. I had made a mistake. No, there's a problem with Maple, with Mobius. So 3. Okay. Thank you. Sometimes my z and my 3 look almost the same. Sorry, that's just the way I write. Okay. People pipe up on YouTube. They go, "Your z's and your 3's," and they go, "It's not z, it's z." And I'll like write back and they go, "You stupid Brit." I'm like, how dumb are you? You know, you stupid Brit. Yeah. Questions? Is that what you were going to say as well? 3? I was missing a 3. Thank you. Okay. So as long as you can do the partials, you should be fine. Okay. All right, let's look at another one. Aha, directional derivative question. This is good. Okay, so this is something we've just done. So let's reinforce our knowledge with computing directional derivative. Okay, these questions are usually very similar. And it's just about, you know, working through them. Okay? So function of 3 variables. Find the directional derivative at the point P in the direction of this vector. Okay? So for this one, let's first of all find the gradient vector or the grad. Okay, so for that we differentiate and form a vector. Okay, so 3 components, 3 derivatives. So let's work it out. So the first component's going to be something like 1 on y cubed plus log of that mess. Yeah? Tell me if I make a mistake. D phi dy. Okay, so that's going to become -3. Something like that. And there's also a y in there. So it's going to become x over y plus z. I think that's right. Okay, I'm differentiating a logarithm. Yep. And then let's work out the third part. So there's no z's there. 1 will come to the front. So it's going to be x over y plus z. Okay, so it's a bit of a mess, but let's work out how we can simplify that at our point P of interest. Over 1. Okay, so that'll be 0, right? Thank you. Let me move that up a bit. Okay, so now let's look at V. What's that? So here's my x, here's my y, here's my z, right? So, oh yeah, that should be 3, so that'll be 3 cubed. Is that right? 3 cubed. Yep. 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 Y plus z. Yep. Yep, I think that's better. All right, thanks folks. Okay, so onto the vector V. Length. Okay, so to get the length we square the components and we're going to divide by that. So 2 squared plus 2 squared plus 1 squared. Okay. So root 9. Okay, so what's our directional derivative going to be? It's defined as this. Okay? Now, a good question here is why is it that? Why is it that? I showed you a picture, but why is it actually that dot product? Why is it actually that dot product? Why is the slope of the tangent line that dot product? I'll tell you in a minute, okay? So that will be the same as this. Yep. And so it's going to be okay, so now it's just a matter of doing the dot product, simplifying. So I'll bring the 1/3 out the front. Okay. You can simplify that if you want to. We've got a number. It'll give us the slope of a tangent. I haven't simplified it. You can simplify it if you want. But let's go back to the more interesting question. I showed you this picture before. Right? We've got a surface, we smash a plane into it, it forms a curve, we find a point on the curve, and then the slope of the tangent, right? Let me show you, at least give you some justification on why this is true. Okay? Let's say I was looking at that combination. So what is this? This is the derivative of some surface in the direction of this vector, which is also unit length. Okay, let me write this out, because I think you'll see something pretty interesting here. What is this dot product? If you simplify this, what do you get? df dx, right? The derivative. So, the derivative that we learnt is a special case of this general directional derivative. What direction is it in? It's in the direction of the vector I. Right? So your plane's going to be, smashing into the surface. You'll get a curve, and the slope. Sorry, dx, not dx, dx. That's what you're going to say.
So it's sort of like df dv-ish. So it's sort of like df dv-ish. That's it. That's the entire question.
Okay. So df. So what's v here?
Like v being the vector that we're.
Yeah, exactly. So you can think of this as being some unit vector, right? So it's in this case it's I. So in this notation you can think, oh, df dx is just that. Okay. Now it's quite a hard concept to get, because there's a lot of visuals going on, and if you can use GeoGebra or Desmos or something to plot some of the surfaces and look at the intersections, it's super helpful. It's super helpful. Okay? So what about if we changed our vector in this bottom bit? Okay? And we went with this. Okay, now we've got a different vector. What's that going to give us? It's going to give us df dy. So there you go. We've recovered what we knew from the previous lectures in this new directional derivative setting. Questions? Comments? Observations? Criticisms? Huh? You're very late. Is everything all right? Oh, have you got a class here now? What is it? Is it any good? You're here like 20 minutes early. Yeah, you love it? This is math. This is engineering maths. Yeah. So, questions? Let's have a look at home. See what's happening at home. What have we got at home? Anything? Oh, okay. Good question. Good question. Why do we multiply by the unit vector and not any other vector, right? Why do we have to sort of normalize it? Well, we need some sort of like idea of a per unit change here, right? Because if you change the length of your vector and you do a dot product, you're going to change your answer, right? You would expect that there's only going to be one answer for a slope of a tangent, right? By normalizing the vector, you're making the answer unique. There's only one answer, okay? If you don't normalize it, you could have a vector, I could have another vector, and they're sort of pointing in the same direction but different lengths. We'll get different answers, okay? And that's not what you want, okay? That's definitely not what you want, okay? So if you don't, and I'll tell you just from a practical point of view, when you're doing the tests, what's one of the things that people forget to do? They forget to normalize that vector. They forget to do it because they're like, oh yeah, dot product. Yeah, I can do this. Oh, no. It's one of the biggest mistakes because people are stressed. They're stressed out. They forget about the little vector. Okay? This is so cool. It is cool. What happened to our log 1? Log 1 went away because log 1 is 0. It disappeared. It's a magic logarithm. All right, more questions, more questions. Comments? Okay, is this a question you could put into GeoGebra, or would it require some kind of model? You could put this question into GeoGebra. I don't think there's a command. Let me show you how I set it up. Okay? Because I think pictures are very compelling, right? So let me show you. So I'll just go back one more time. Okay, the first thing I plotted was the surface, because I want to know what it looks like. Okay? That's the first thing I did. Right? The second thing I did was I drew the vector. Okay, you just use the vector command. Okay? Third thing I did was smash that with that plane that's containing the vector. Okay, I get a curve. The last thing I did, that point is the point that we're given that lies on the surface. Okay? That's how I did it. Now, can you solve these using GeoGebra? Maybe. You'd have to fit a tangent line to that curve at the point A. Probably GeoGebra is smart enough to do that. You just have to work out the slope. Okay? What else have we got? Sorry, I asked the question when you were doing that, as you now have 3 inputs and not 2. Okay, let me see if I can understand your question. I asked that question when you were doing the scalar field. Yeah. So the scalar field, let me go back to that one. Yeah. Yep, let me go back here. So that's a function of 3 things, x, y, and z, right? I don't think you can rearrange that very easily to make z equal a function of x and y. Okay? So that may be quite difficult to plot. Yeah, displaying it. Sometimes GeoGebra can display stuff, sometimes it can't. Okay? But just try. Just try. Okay? All right, other questions? Yeah, okay, I get it, yeah. So obviously 4-dimensional things are going to be very hard to plot. You can do it. Let me show you. No. No, even simpler than that. Well, you can. That's probably a discussion for another day. But yeah, go there. Leave. I don't care. Leave. I said leave. Okay. So one way of doing this, let's say I'm just going to go back to a standard one. The balloon. Give me the 3D. Oh, you stupid thing. Okay, you can handle that. Let's add one more. It can't handle that. It can't handle that. Let me put this on for everyone at home. So I've put in x squared plus y squared equals z squared. It can't handle it. But what it can do, it can handle when that is equal to different constant values. So you might have seen the slider function. Let me see if it works. So let's say this was, I don't know, equal to 1. Okay, let me try again. Okay. So for a particular value, you can plot it. Okay, this is called the level surface of x squared plus y squared equals z squared. And then you can even form a parameter. So instead of 1, you have a parameter and you can shift the parameter. The balloon gets big, the balloon gets small as you vary it, right? So sometimes you can plot these things, but not always, okay? And they vary, you know, maybe they vary over time or something, okay? So my advice is to just play around with this, play around with Desmos. My personal view is that this is much easier than Maple or MATLAB, and the graphics are better, right? Has anybody ever plotted in Maple? Right? It's okay. It's not as good as this, right? I like Maple, I enjoy it, but for pictures, this is better. This is better. All right, great to see you all again. Well done on finishing week 2. Let's finish there. Come down if you have any questions, and I'll see you next week, okay?